All right, welcome back. In this video, we're going to look at our takeoff analysis and plot our thrust weight ratios for a takeoff ground run requirement or for a total takeoff distance requirement. And we're going to use the takeoff parameter method. We'll also use the method introduced in Goodmanson. So first, let's just talk a little bit about takeoff conditions and what happens in takeoff and what we're considering. So I like this figure from Goodmanson text. Plot that here just to get a sense. These are the phases of takeoff. So depending on the classification of aircraft and how it's being certified, you can define your takeoff as a ground run distance and a total takeoff distance. Your ground run is essentially, how long you're traveling along the ground. So your wheels are in contact with the ground, minus this rotation. So when you have all wheels in contact with the ground. And your total takeoff distance is includes the additional distance it takes to rotate your aircraft to start generating enough lift for all wheels to leave the ground, and then the distance traveled when you are climbing over some obstacle. So depending on the requirement, it might be a 50-foot obstacle if it's Part 23 certified aircraft, or Part 25, 35-foot obstacle for takeoff conditions. And we define this liftoff speed based on the stall speed of the aircraft. So our liftoff speed that we use in our model is coming from requirements of Part 23 aircraft. This is determined as 10% more than the stall speed of your aircraft. So we'll include this as your stall speed that we have in our requirements above times 1.1, and that gives us our liftoff speed. Now the equation is represented by Goodmanson. If I pull those up, maybe I can add this to the screen so we can see it. Plot that here. This is the thrust to weight ratio equation based on our wing loading and a few other parameters to determine our ground run. So we have some of these coefficients were just simplified from values from the analysis. You can look at the textbook to determine how those were determined, but our CL max here is the maximum lift coefficient that the aircraft can generate in the configuration. SG is our ground run. We have CL max for our takeoff condition, so our max lift coefficient in our takeoff condition, and then we have our drag during takeoff and our lift during takeoff, our coefficient of lift, and then these mu parameters of the coefficient of friction, which is quite low in the takeoff condition. It's just mostly due to rolling resistance, so you can approximate that. The text recommends 0.04. So I'll leave this equation up here. I'll get rid of this figure, make this a bit smaller. So if we start with the Goodmanson method, I'm going to create another column here. It's going to be called takeoff, and I'm going to do ground run. So we have a ground run specification. And it's going to be at sea level, and what we're going to be plotting here now is thrust to weight, so our TW ratio. Again, I'll just center this. So we're going to plug in this equation now. So to go 1.21 divided by, in Excel, if you have a numerator or denominator rather, you should put those in brackets so that you're not inadvertently multiplying by values when you think you're dividing by values. So divided by G, put everything in here. If we wanted to change G to see what it would be like to try to take off on Mars, we could do that. Times our density. Now we're doing sea level, so our density at sea level is up here. Times our CO max. So our CO max in our takeoff condition, put that over here, 1.5. Close brackets, times our ground run. So one of our requirements, I have ground run distance. I just calculated this as our total distance divided by 15%. If you look at trends in data from total takeoff distance over a 50-foot obstacle and ground run distance, you can sort of plot this trend ratio. I just use this as an approximation for now. So let's say our total takeoff distance that we are desiring is 4,000 feet. Our ground run, I can say, is about 15% less than that. So take the total divided by 1.15. This is our ground run distance. Close bracket, and we're going to multiply this by our wing loading over here, our x coordinate, plus 0.605 divided by our max lift coefficient again, times, now we have our drag during takeoff and our lift during takeoff. So this is our average lift and average drag during takeoff. Now the values I have in here are calculated from something previously, so I'm going to change those, but I have those parameters here, lift coefficient and drag coefficient during takeoff, so I'll put those in for now and we'll talk about them. So I have drag during takeoff minus lift, oh, did that wrong. Drag during takeoff minus lift times our rolling friction coefficient. And we want to make sure we use the right one. There's one for landing, which is 10 times higher approximately than the one for takeoff. Takeoff, we're not holding the brakes down, so our friction coefficient is low, whereas landing, we have a lot of force generated by friction due to the brakes. We have a higher mu. Close bracket, and then we add our friction coefficient again, at the end. Hit enter, we get a thrust to weight ratio of 0.12. This is a reasonable value. Based on these parameters, we have a really high takeoff lift coefficient. So that could be why we don't have much requirement for our engine power. So again, I'm just going to add dollar signs in here. I'm sure there's a faster way to do this, but I'm not sure what it is off the top of my head, so I'll just do this. And the only value we're not going to change is our wing loading, so I'm going to leave that without a dollar sign. So then I double click on the corner here and it auto populates the remainder. You can see it is changing with wing loading marginally. So let's add this and then we'll play around with some values. Select data. I'm going to choose takeoff. And I'm going to indicate that this is Goodmanson. Let's put Goodman. Our X values are our wing loading values. I'm just hitting Command Shift and down. That's going to highlight everything. And I'll do the same thing for the Y values, or thrust weight ratio values. Control Shift down. That highlights everything. We're good to go, and we have our plot. Now, if we look at the form of this equation, we have a slope times our X coordinate value plus some intercept value. So we should have the equation of a line, and we do. It turns out because our CLmax is so high and our ground run requirement, these values are not a very high slope. So it is not very strongly dependent on our wing loading. It's much more strongly dependent on these values. Now that could be because these intercept values are also so high. So let's look at what how these values affect our curve. I talked about our lift during takeoff. I calculated this based on an assumed wing loading. So I'm going to change this, and I'm going to use a nice table presented by Goodmanson that just gives some average values for your takeoff and landing coefficients, and it also gives an approximation for your minimum drag. So I'm going to use this. If we look at this table, just copied this from our notes, from the textbook, we have the drag coefficient during takeoff for various types of aircraft and the lift coefficient for takeoff. And this is assumptions, flaps in the takeoff position. So let's assume we're trying to model a modern passenger jetliner. A minimum drag, we can choose somewhere between 0.02 and 0.028, depending on how conservative you want to be. Maybe we'll choose 0.025. And then I'm going to choose the drag during takeoff based on my lift during takeoff. So I'm going to choose a lift during takeoff, and then I'm going to use our drag polar equation to calculate the drag during takeoff. So I'm going to put lift during takeoff as 0.8, and CD min, I'm just going to put that in as well as 0.025, somewhere within that range. So let's see how this changes everything. Let's change this to 0.8 for our lift coefficient during takeoff, so that moves down dramatically. We can see our drag during takeoff now. This is based on our drag polar equation. So our drag polar equation, we have our minimum drag plus our lift-induced drag. And our lift-induced drag, using the simplified drag model here, recommend that you use the adjusted drag model for your aircraft, but for now I'll just show simplified drag model. We have the lift coefficient squared in the condition, so 0.8, divided by pi times the aspect ratio times the span efficiency. Now I use the equations that presented in both textbooks, just assuming a straight wing to estimate my span efficiency. I also just showed for comparison the span efficiency for a swept wing using the swept wing equation, and I assumed an angle of sweep of 30 degrees. So we can see for the straight wing design with an aspect ratio of 10, and it's independent of taper ratio, so it doesn't come into play. But if we have an aspect ratio of 10, this equation might tend to underestimate a little bit, but we have a span efficiency of about 0.75, 0.76, and an aspect ratio of 10. So I'm using that to calculate my drag. And if we compared that to the table we just looked at, the drag in the takeoff condition for that class of aircraft is about 0.03, 0.035. So we got a bit high value, and that could be because our minimum drag value is high. Now I chose 0.030. If we change that to 0.025, like I suggested, we get a bit of improvement here. But this could be partially because we have a low aspect ratio. Well, it's not a low aspect ratio, it's a fairly high aspect ratio. But it could just be because this approximation for our span efficiency perhaps is underestimating a little bit. And we're also not accounting for our corrected aspect ratio. We don't have any winglets or end plates or devices that are going to improve the span efficiency, and it doesn't take into effect the taper ratio. So this might be under predicting a little bit. Let's say we choose a value of 0.8. Span efficiency of 0.8, then our drag during takeoff decreases a bit further, 0.9, we get around 0.47. So I'll leave it as the equation for now. It's something to play around with, but once we know our lift during takeoff, we can assume a drag during takeoff. We need our liftoff speed, and that's to calculate just to get a sense of what our liftoff speed would be based on our stall speed. So I just took the stall speed requirement, which was up above. We still have it at 90 knots. And so 90 knots times 1.1 gives us our liftoff speed. So when I was talking about that condition for takeoff, that's the speed we're looking for. All right, so we have a thrust to weight ratio plotted using those values. Let's look at the effect of maybe our ground run. If we change our ground run, how does this change our slope? Let's make our ground run requirement maybe much smaller. It has to take off in 2,000 feet over 50-foot obstacle. And we can see that the thrust to weight ratio has decreased 0.04. Let's increase this now to 4,000. What is going on here? This thrust to weight ratio is way too low. All right, we have our wing loading divided by acceleration due to gravity in feet per second squared, our density, our CL max. I'm missing a value here. Times our ground run. CL max G, maybe I'm missing density. Yeah, I'm missing our density value. That should make a big difference. There we go. So we can see now, based on our wing loading, our thrust to weight ratio requirement changes much more significantly. So we actually have a positive slope. So last time I was not dividing by our density, which is a very small number. So if we divide by a smaller number now, we have a much larger slope, which is what we see here. So we get something that looks a little bit more realistic. Now let's try and plot the takeoff using the takeoff parameter method. So I'll write takeoff, and I'm going to write in here TOP for takeoff parameter. Again, we're going to look at sea level conditions, and it's going to be plotting our thrust to weight ratio. Now our takeoff parameter, if we look back at our plot that I saved over here, we have our takeoff parameter. I didn't put titles in here, but we have this figure over here. So takeoff parameter is defined as our wing loading divided by our density ratio, our lift coefficient during takeoff, and our thrust to weight ratio. So if we rearrange these equations, we end up with this relationship. Our thrust to weight ratio is equal to our wing loading divided by our takeoff parameter times sigma times our lift coefficient during takeoff. So we're going to code this in. Now our takeoff parameter, again, is a function of our landing or takeoff distance requirement, and we've already coded that based on whatever landing distance requirement we have by plotting that function or that best fit line from the Lofton figure. So let's write in equals our wing loading divided by our takeoff parameter, TOP, times our density ratio. Well, if we're doing this at sea level, our density ratio is just going to be equal to 1. So I'm going to leave this out and multiplied by our lift coefficient during takeoff. That is 0.8. And we get a straight line relationship now with no intercept. So we have a slope. Essentially the slope is 1 over takeoff parameter times our lift coefficient during takeoff. And so if I copy these over, we have an equation for our line. I'm going to add this to our plot. Takeoff parameter method. We have our x values. And our y values. So again, the takeoff parameter, very sensitive. Thrust to weight ratio is very sensitive to this takeoff parameter. So if our takeoff parameter is, fitting a data set, the data set that we use is quite important. So if we use the data set from Raymer, for example, we might get a different value. So maybe it would be useful to plot the trend line for takeoff parameter from the Lofton reports, or Roskam is also another one that you could use. I think they're based on the same data set. And then you could also look at Raymer's, which also draws from these data sets to generate these more generalized lines. So let's just compare visually for now. We have our requirement for a takeoff distance over a 50-foot obstacle is 4,000 feet. So if we go over to our Raymer figure, our takeoff distance, 4,000 feet, somewhere over here. Move horizontally to our curve for a jet aircraft. It might be somewhere around here. So we go down, our takeoff parameter is just under 200. So let's say, 195 would be our guess. So let's compare that to the value that we've used in our analysis. The value we've used here is 96. So there's quite a large discrepancy between these two. So if we were to change this to 200, let's go back down and look at our constraint analysis now, our diagram, and see how that changes. Maybe I'll leave it in the screen so we could see how it changes in real time. So takeoff parameter is 200. Takeoff parameter is 96. giving myself a headache. All right, try this again. We have takeoff parameter right now just under 100. Change the takeoff parameter to 200, and we could see how that reduces the constriction of that requirement. So a higher takeoff parameter is going to give you more design space. Essentially, anything above this line is an acceptable design point. We have enough thrust to take off in the distance given, and enough wing loading to take off in the distance required. So whichever method you want to choose, maybe this means that we have a longer takeoff distance requirement. We can't take off within 4,000 feet. Maybe we have a takeoff distance of 8,000 feet. So again, our stall requirement is basically limiting our maximum wing loading. So if we really want, we could go back and adjust this and now change our maximum from 140, and maybe I want to make this just 60. Even smaller than that could probably be okay, 50. So we're starting to get a picture of our constraint analysis. We have our stall condition. We have 2 takeoff conditions based on 2 different models to give us a bit more confidence. We might have to do more investigation in takeoff parameter and making sure we have some realistic CL max values for our aircraft. I'm recommending just reading those sections of the text and the notes so that you're inputting the correct parameters for your aircraft design. So in the next video, we'll look at our climb requirements and how to calculate climb. It is an iterative process. One of the equations for best rate of climb depends on a thrust-to-weight ratio. So I'll show you how to change settings in Excel to allow for iterative calculations so that you can estimate your various best climb wing loadings and thrust-to-weight ratios based on the equations presented in class.